there's the seating chart. Enough said. We will move on from the seating chart. There we go. Okay, so we talked about approximation. We talked about accumulation, and accumulation is taking a rate of change function and taking a look at the region between that and the x-axis, and that gets us information back about the original function. Right, we're looking at that rate of change, and we're accumulating between it and the horizontal axis. So, and now we're talking about how does that approximation, how does that Riemann sum look as a summation notation? Okay, so summation expressions are typically for equally sized intervals. So the delta x's are the same. The approximation becomes more accurate as the rectangles get narrower and more plentiful. So that was that animation you saw in your notes, where I started the animation and the rectangles this wide, and they started getting skinnier, right? Then we started to see that we could more accurately represent the space between the function and the horizontal axis. Definite integral is the limit of that Riemann sum. So the exact value between the space and the horizontal axis is taking a limit as we put infinitely many rectangles in that space. Okay, that is the definition of the exact value. We call that a definite integral. It would be nice if that space were geometric, because then we wouldn't need calculus at all. But life is not that nice on occasion. We'll get to that a little later on in the unit. The exact area of the region can be written as either a limit of the Riemann sum or a definite integral. Although writing it as a definite integral is much easier. Questions about those takeaways from the notes. So I'm going to be checking off notes. So if you're at home, you're going to be sending me your notes in WebEx. So how can we make the approximation more accurate? Any ideas? Apparently it's Shane. Awesome. That's very mathy. More rectangles. Right? Subinterval is a rectangle. By using a ridiculous number of rectangles. I took the non-mathy route when I wrote that. And then I kind of copped out on the second question. How do we express definite integrals of sum by using the summation notation in my notes? I think if you just go back and look at that summation notation, that's a little more meaningful than trying to squeeze something in a little box at the end of your notes. I could be wrong. Okay, so we have a couple of things to do. Well, we are back to 1 hour classes, right? We're back to our drop schedule. So this ought to feel like, oh, I've got so much time now. Instead of 40 minutes, I always felt like I was sprinting. So we can really do our due diligence on the topic questions with this sort of time frame. Okay. Okay, so we have an accumulation quiz in College Board. And then once you get done with that, you can stay right in College Board and do your day 4 topic questions. And there's a free response along with that. And that rubric is in Blackboard if you want to check your answers. I'll be around though, so we can talk about those things. Okay? And then I'll come around and check your day 4 notes sometime during the class period. Okay, so first on the list of things to do is get that quiz done. It's a 4-question quiz. That's why it's 8 minutes. Any questions? All right, go for it. Go ahead and log on. I'm going to hang out here in College Board, my own little College Board world. Make sure you're all in that quiz. Can't wait to go home and snuggle. I love snow. One of those people. Oh no! Oh. Oh. Where's your car? Is it close? You wanna run out and do it? Okay, I would let you. Uh-huh. Have you been? Oh, yeah, have you been doing this? Okay. So, but yeah, so I use that too. So like, for instance, is it 4 times or 3 times? So, yeah. So, I, so if I look at this, the first type is 2, and then this next type is 7, and then this next type is, and this last type is 5. Definitely 3. This one's definitely, we're going to be integers. So this is definitely 3. And this one is definitely 4. Okay. So the idea of the trap is, so the biggest trap is, if I'm going to hold it like this, you can stand your ass. That doesn't feel good. Okay, you see the trap again? Okay. So this is the whole. If you only put the trap goes up and and so we have height, base 1, base 2. So 1.5 times the quantity of this. And the next one is this. And the next one is this. We also have to use this stuff and use this stuff on the end. So what we do is a 1.5 times the big quantity of this. That's the math shortcut to make the math a lot. Yeah. Alrighty. Oh, we're logging out. Let me know if you have any questions. We're all kind of waking up here. Busting up the cardboards. So we should all be in the quiz right now, just to clarify. Finishing up with the quiz, go right into your topic questions. I'll be around in just a moment to check out notes and answer any questions you might have.
Thank you.
that differentiates what used to be delta x in the summation notation. So it's an really skinny rectangle. It's a result of, it's basically at that point, because we're looking at the rectangles, because we've expressed it as definite interval, it's saying basically at this point it's not functional. Saying we're going to write whatever we see here in terms of x. Okay, and then we're going to do something with that eventually using calculus, and then it will be significant that to make sure that this x, and it's an x here, it's an x. So no, this is your delta. So what that basically says is we are 205. So let's see. First of all, let's see. So that 2 points. Sometimes we start at 0, like sometimes So I'll make we start at 0. Um, yeah. Because so first, so the since it starts at 1, so it starts at 0. Yeah. I mean, it's not like a good but I can be. Oh, how can I do that? I gotta go here. No, no, go here and here. Oh, are you in top questions, right? Yeah. Okay. 3, 4. It's the square root one, right? There it is. Yeah. Deep. Uh-huh. Because K started at 1. A left Riemann sum would use the left side of the rectangle, so it would start at 0. Yeah. The left Riemann sum would start at 0. It would start with the x of 0. Do you want to see the explanation? Oh, you'll see the explanation when you submit it. So all three of those would be equal. All three of those is a way to rewrite it. So if you notice, K started at 1, right? And if K starts at 1, then we are not starting at -1. We're starting on the right-hand side. So we're starting at 0. Okay, so that is, so to keep it the way it looks, you started at 0. Because again, since K is equal to 1, it's a right Riemann sum. And the right Riemann sum is going to use the right side of that first rectangle, which is not going to be at 0. It's going to be x1 over. It's going to be delta x over. And then we know the width is 5. So that, I think that makes 2 an obvious yes. It is 1, 2, and 3. Yeah. So it makes so 2, it makes 2 obvious. We're on number 1 on the topic questions if anyone's figuring out what we're talking about. So so that makes 2 an obvious yes. And then we can rewrite it. If we want to rewrite it as an LRAM, we can back up to the -1. But if we back up to the -1, that means the -1 has to come out of the expression because we moved it to the left. Moving it to the left is like adding 1. That makes sense? Oh. So remember shifting functions. If we shift them to the left, we add 1. If we shift them to the right, we subtract 1. So if we want to shift this to the left, we're going to take the stuff in the brackets and add 1 to it. But we have -1 plus 5k over n, and then if we add 1 to it, then -1 and plus 1 are canceled out. And so you just have the sign of 5k over n, which is just your x. Because your 5 over n is your delta x, and your k is your counter, so to speak. And then 3, yeah, 5 is a multiplier, and that goes back to your trig identities. Yeah, that one's really pulling from yeah. That one's really pulling from some sketchy trig stuff. Are we done with 1? Okay. Yeah, sure. You're right. You're right. For 3. Yep, you're right. Yeah. Not so much work. It's more, it's more possible. So you're just totally not as a